Hi Brian, it's lovely to be back at the NXP stand. It's Embedded World 2023, and every time I meet you, you've got something new to share. So
that's true.
What's going on? As we always know, we had you on the Engineering Insights show talking about automotive and all the development and advancements in automotive to make a sort of software-defined car. What chips are you bringing out now, and what difference are they going to make?
So we talked about the brain of the EV. We talked to the brain of the motor, electric motor, and now we're talking about the brain of the complete vehicle for vehicle computers and high-performance safety. So what we did is launched our S32G3 family yesterday here at the show, which takes our S32G family overall to a much higher level. So we have the S32G2 series and now the new S32G3 series, which has 2.5 times the performance, the memory, the networking, and really takes it to the next level that's required for software-defined vehicles and more of these high-performance ADAS and autonomous vehicles for safety processing. So that's what we announced here at the show yesterday. It's in production and actually in some vehicles today. Yes.
So give us a bit of an idea then, what's actually inside the chip? How many cores do we have? What sort of memory? What sort of connectivity in order to make all this possible?
Yeah, great question. So this is actually a combination of safe compute, networking, a lot of networking interfaces, networking acceleration, and it's built on a foundation of functional safety. It supports up to ASIL-D systems, and it has embedded hardware security engines, so it's bringing all those together. Right. Now, if I talk about the cores themselves, there's actually 30 cores in this device. It's pretty amazing. Actually, this is the device. It's a 19 millimeter package. So incredible. All of it's in that little package. Yeah. There's 21 ARM cores. Of those 30 cores, 21 of those are ARM cores. Yeah. And there's a combination of real-time cores, Cortex-M, and application cores, Cortex-A. Yeah. So this part is fairly unique because what it does, it's not, there's parts that are microcontrollers, there's parts that are application processors. This brings all of that together, so it's a combination of that with networking acceleration. So now I can accelerate 16 CAN FD channels. I have 20 on my chip, 16 can be accelerated. I have 4 gigabit Ethernet ports, and 3 of those now with this part are 2.5 gigabits per second. Okay. I can accelerate those, I can manage the data, I can manage all those packets and do it very efficiently. So all those cores, even though I have all those cores, they don't have to deal with all the busy work with the data. They can be handled by the network accelerator. So that's really what's key about this part, is lots of real-time application processors, plus networking, plus accelerators, and all built on functional safety and security.
Now, when we've spoken in the past, and when I've also talked about with other people on my show about the automotive, what we're seeing is the architecture of the car is changing.
Yes, definitely.
And there's sort of two competing ideas. Either we have a domain controller where we have processors handling different domains of the vehicle, like braking, steering, bodywork, chassis, or then we have the zonal process. We have a really powerful processor in the middle, and sort of functionality could even be distributed across several ECUs.
Yes.
Now, is this device targeting one of those, or can it support both architectures?
Yeah, that's an interesting thing. There's actually, I don't know if they're necessarily competing. Sometimes it's evolutionary, and sometimes they work together because I think this is a process. It depends on the OEMs. Every OEM's a little bit different. And if you look at the evolution of this, or revolution to zonal, sometimes it actually happens in steps. Sometimes people can move faster directly to zonal. So for us, we're agnostic because we design these parts to be able to support both those types of architectures with the compute, with the networking. But what's really important, it's the common denominator of that is consolidation, integration, and cross-domain integration of multiple functions sometimes. That requires a new type of SoC or new type of processor, and that includes isolation. So I can have multiple tasks. Like today, it's isolated by boxes, right? ECU and ECU, they're connected by wires. What our chips do, and like we talked about last year with the Z&E, is that they're isolated inside the chip, isolated in hardware. So we're doing that today. That's really important. So for our perspective, we can support domain or zonal, or there's combinations, hybrid. I mean, some of it are starting with body, where they're putting body in zones or electrification zones, and then the whole vehicle may be zonal over the next few years. So it doesn't always happen at once in those cases. So we're pretty open into it. It's definitely a hot area, and that's why these chips are really popular, because the G, you said, where does this fit in? So the G2 and G3 fit in that central computer or the gateway functionality that are bringing the whole vehicle together, all the data, not only the secure networking within the vehicle, but secure connectivity to the cloud, working through the telematics unit. So it's the heart of all the data flow, secure data flow through the vehicle. because it has all the application processor, it can now do services. And we're actually showing this with the G3 here, is we can actually put services on top that can be deployed through Kubernetes data center type technology within the car. So it's really the heart of all of these, whether it's a domain architecture where it's the gateway and the master brain working with domains, or it's the vehicle computer that's doing the overall vehicle strategy and working with zones to do the actuation and sensing. We do both, so it doesn't matter.
Now, one of the interesting things we're seeing in the automotive space, as we've discussed before, is the software-defined vehicle, and the key element, and we were talking about this, about the electric motor platform as well. When I buy my car, I'm going to have the worst performance electric traction than I'll ever have over its lifetime, because the software will be updated. Yeah. But I think one of the challenges we have in the automotive industry, typically when the ECU is finished, we ship it and we don't touch the software again. Right. And you just mentioned cloud, Kubernetes. What are we learning from cloud and sort of containers and software updates and live updates on systems, and how's that moving into automotive?
And this is a huge area. We could do a whole episode just on this. So there's multiple angles for it. Let me talk to at least a couple of those. So there's within the vehicle, so we're talking about the Kubernetes and having an infrastructure, so you abstract the hardware and software. Basically, you're just layering these things on, and they're isolated, they're containers. That's one angle to it. There's also the over-the-air updates of discrete functions that are not containers necessarily. It could be complete virtual machines, it could be the whole system, it could be a core in the real-time section. That's an over-the-air update process, and we support that too. Typically with partners, we have multiple partners that allow us to do that. So there's that whole process. Now what's the key thing with OTA, I think you referred to, is that a lot of times these ECUs are black boxes. Typically they're very I would say limited in capability, limited in security. Maybe they only have symmetric cryptos. They don't have asymmetric cryptos. They don't support digital certificates and public key infrastructure. So that's the challenge today with today's vehicles, is that they're closed boxes. They're not updatable. They're never intended to be updatable. And so what the SDV is doing is actually making those software functions with common security, whether it's the G, the Z, the E, or the K. From an NXP perspective, we can do end-to-end vehicle over-the-air updates. And we have one of our partners, Ubiquiti, has a suitcase, a car and a vehicle that has all of them in a box doing system-wide upgrades. It just shows that once you have parts like what the S32 types of parts that have, asymmetric crypto, support public, even doing post-quantum crypto today, we're showing that, but have a common security architecture where whether I'm a supercomputer in the car or I'm a small little microcontroller in the car controlling lighting, all of those have security that can enable end-to-end security and over-the-air updates. That's critical because you want to be on public key infrastructure, just like everything else in the world today with certificates. Gives you a lot of flexibility, a high level of security. So the future is going to be over-the-air updates throughout the system, vehicle-wide over-the-air updates, and then like this, the Kubernetes containerization types of deployment of services. And where the cloud comes in, the cloud is critical because now the OEMs in the industry are using the cloud to do virtual development. So I could do all my software development on our chip in the cloud, not even having to be on hardware, develop the software, test it out, do integration, and then deploy it through over-the-air updates to the vehicle and the chip. I know Sophie and ARM and all these companies are working on this environmental parity so that they can run software on S32G or these types of parts in the future in the cloud and then deploy it to the vehicle. And that's that whole CI/CD, continuous improvement, continuous deployment, and the ability to have this whole DevOps flow for SDV because you want to deploy it through the life of the vehicle, which is over a decade plus. So there's a lot of complex, like I said, we could talk about this for a whole episode.
Exactly, we were talking to Robert Day at ARM about Sophie. So what's NXP's role in that project, and how are you going to contribute to that? How's it going to contribute to you?
Yeah, definitely. So that's one of the important initiatives that are going on. I mean, NXP is really heavily involved. I mean, we're a thought leader involved heavily in SDV. Sophie's a key part of it, also Eclipse Foundation and others. For Sophie, we've heavily involved there. I think we're showing these kind of capabilities, working with Sophie, with AWS, with ARM, and all these types of members to bring, because it takes a village, right? It's an ecosystem to bring it all together, and our platforms are really attractive to do that, to start to showcase how can I deploy these into Kubernetes or containers, or how do I extend this into the real time? So we have the S32Z and E, as you know, and the Green Box 3, and how that gets extended in. So I think we're going to be a key partner in that with the hardware platforms and working with our cloud and other partners in the ecosystem to really make SDV reality and to streamline the whole process. I think the key is going to be how do we standardize some of these? They're non-differentiating per se, right? Is how we make the infrastructure work on top of hardware that under the covers is really optimized for doing all these things that have to happen. That's the differentiating part, the silicon, the software, the ecosystem can provide the non-differentiated part, and then the innovation on the top level, the software-defined vehicle now explodes, right? So you need that layer, which is what's important that Sophie is helping to standardize to make that happen. So.
Well, every time I talk to you, Brian, I keep thinking I need to put off buying a new car because I want to make sure there's NXP inside.
There you go, appreciate that.
Thank you ever so much for the update, and wish you all the success with this new product, and hopefully we'll have you back on the show shortly.
Definitely.
To
our next innovation.
Yeah.
And thanks for stopping by again.